Good afternoon. Welcome to I think that's the third lecture of the class. Now we start to first give a bit of preliminary information on the base filter, some tools, and something that the students that have been at the Introduction to Mobile Robotics have seen already, but as a recap, it's good to then start from the same background. Okay? So the lecture today, the first hour will be on the base filter, and we'll give a small recap, short recap on motion models and on observation models. And then the second part of the lecture will be about the Kalman filter in general, how it works and how one can use it. And then from next week on, we'll start already with the first SLAM algorithm, which is the one based on the Kalman filter. Okay? So what is the main core of this lecture? We've seen this word state estimation already during the introduction when I was telling you this problem is related with what people call state estimation. And the goal of state estimation is that you have a set of measurements and you have an unknown state of your system, and you want to know which is the current state of your system, or at least you want to have an idea on where your system can be. So the goal is, assuming X is your state, and you have some exteroceptive measurements, which are Z, and these are measurements that come from the outside world, and some proprioceptive measurements, which is U, which is something that measures yourself. And you can imagine these are like the measurements that you can obtain if you just do not touch anything, you close the eyes and you walk around in the environment. And this one is the measurements that you get by just touching things or looking at things and so on. Okay? And the goal is we have these two types of measurements and we want to find a distribution. So this P is to say we want to find the probability density function over the state. Okay? And normally we call this Z here the observations, and we call this U the controls, because somehow it's what moves the robot around. But you can also imagine that this might not be the exact control, but it's what the robot measures after he makes an action. So if you have like wheel encoders on the robot, which are some sensors that measures how much a wheel turned, this can be still modeled by a U here. They kind of have the same form, but it's not exactly the real control that you gave to the robot. No? But for now, just abstract it and just say, we call this control, but actually means what the robot observes directly of its state without having anything outside of his field of view or measuring something which belongs to the environment. How do we do that? One way of doing it, and actually, let's say one general class of doing it, is what is called base filter. Okay? So the base filter starts by defining what is called the belief over a state, and the belief is nothing else than the distribution of the state variable at a certain time t, given all the measurements that you obtained through the beginning of the time. So this Z1 colon t means these are a stacked vector of all the observations that I obtained at time 1, at time 2, time 3, up to times t. And also considering the control. So again, this U1 colon t, it's all the control or the proprioceptive readings that the robot had from the beginning of the time until now. Okay? And again, we assume that we have a time discrete system, so that all this observation comes at a discrete interval in time, and they're all synchronized, that they come at the same, with the same time frequency. Okay? Is it clear? Now, the base filter is a recursive way. So recursive means that at each time step you do some operations, and then you basically build these distributions at time t plus 1, considering what you have already done in times t, times t minus 1, and so on. And it does it by considering these measurements once at a time. So the first thing for getting the recursive formulation is to try to play around with this distribution here using Bayes' rule in a way that we then ends up with pieces that only depends on one time step. and that we know how to model them. So the first thing we do is we apply Bayes rule with the latest measurement. So we put it on the left. We then put the x on the right. So we swap them using the standard Bayes rule. And then we have the second part here that comes automatically because of the swap. And then we have a normalizer up here. So how many of you actually do not know what the Bayes rule is? Raise hand? Okay, so I don't have to write it on the whiteboard. Okay, so you don't know. So the Bayes rule is basically what we use to define where is the cleaning? Is that we use it to know how to go from, let's say, a causal reasoning to a generative reasoning in some way. The meaning is this: assuming you want to have, you have some event A, okay, and you know that A depends upon a certain event B, okay, but you don't know how these two are related directly in this way, but what you actually know is how a certain event can cause a certain cause. So imagine now A is something like the grass is wet, and B is something like the sprinkle is on. Okay, and you want to know how this happens, but you only know how the relation, or let's say the other way around is maybe more intuitive. A is the sprinkle is on, and B is the grass is wet. Okay, you know if you have the sprinkle on, the grass is wet with a certain probability. So actually, what you know is this: is P of B given A. No, so that's like the cause, and this is what you actually want to know. And Bayes rule tells you that this distribution here is actually equal to, you just swap these two guys, okay, and you say it's equal to P of B given A times P of A divided by P of B. Okay, so that's what the Bayes rule says. The idea here is that there is a way of turning from let's say, the evidence to the cause and vice versa. And this is just like what the rule says. And this is true for all distributions, random variables. Either they are discrete or they are continuous, where you change the density with the mass with the density and so on. Okay? If you have a conditioning here, so you have multiple variables on the back, you keep that forward. So if now I will have a C here, I can just put everything back. A becomes A given C, and B becomes B given C. Okay? So that's the basic block of the Bayes rule. And that's the same thing that we did here. We swap zt with x. So the z1 to t, you can see it like a concatenation of all the different z's. We swap the two. So we did this, and you can see it here, and we keep all the others as they are. So z is from 1 to t minus 1, because one of them has been swapped. You get the xt given the rest, which is what we have up here. And the thing which is down here, we just put it in the normalizer constant in this case. Okay? And that's because the distribution we care about is about xt, and with respect to xt, this is just a constant. Okay? So we don't really need to express it directly. Okay? Is it clear? Now, if we go then further on, you can also use what's called Markov assumption. The Markov assumption says that the state holds all the important information of the past. Okay? So once we know the state, all what happened in the past is independent of what will happen in the future. Okay? So this basically means that in this case, since we have xt, we can completely forget about this, because xt has all this information together inside itself. Okay? We go then further, and we use another thing which is called the law of total probability, which basically says that if I can do it on the discrete case, or the continuous case is the same, but it basically says if I have a distribution over a variable A, okay, and I know that the all space can be considered, also considering other variables, I can say that P of A is equal to the integral of P of A and this other variable B in the B, okay? And if B covers all possible space, then this is actually equal to that, okay? We can then go again here and applying what's called the chain rule that tells us that a joint distribution PA/B is equal to a conditional one, PA given B, times PB. No, that's another rule from basic probability theory. When we apply both, this is the law of total probability and this is the chain rule, we end up in this case here. Now, what does it mean in practice? In practice, this means that since we do not know we don't have any direct way of knowing the distribution of the states at time t, given only the control and the previous observations, we can say, okay, let's assume I know where I was. So let's assume I know where I was at time t minus 1. And this is something that I can relate, because with this guy and the motion, I know how much I moved. And then let's put it here, and let's just do this law of total probability with respect to the previous state. No? And we then do the chain rule as said there. And basically we say we have two components. One, it says how much I moved, given that I was here previously. And the other one says, where was I previously, given that I made these measurements? Okay? And since this is something that we don't know for sure, we just take the integral. So we consider all possible positions I have been in the last time step, and we propagate all these possible positions forward. Okay? Now again, we can use, that's one too much, we can use the Markov assumption. So we can say that here the only thing that matters is what happens after t minus 1. So we will remove all the observations and we just take the last motion control. And we can do the same on this other case here, where we say that the next control does not depend on the, so that the previous state does not depend on the next control. No? So that where I was before, since maybe someone is moving the robot around, is not something that will influence where I will move in the future. Okay? And when we have all these things put together, you can see already that there is something here that reminds you of what we're actually trying to do. No? If you look at this here and you look at this here, they look quite similar. And in fact, what happened is that we just have the same belief definition that we had up here. So at the end, we end up with this recursive formulation where we say that the next belief, so the belief at time t, is equal to something where we use the belief at times t minus 1. We propagate it through the motion model. That's what we call motion model. And then we update using the observation model, which is this distribution here. Okay?
Question.
Yes?
Is it possible for us to derive a closed form formulation of the
Of this? Yes. And actually, the Kalman filter does exactly this. So the question was if we can derive a closed form solution for that. Everything here is super abstract. We just talk about generic continuous density. And according to the way you, let's say, model this density, so according to the assumptions you make in your system, like the type of noise, the distributions involved, and so on, some of them have a parameterized family. So basically means that you have an analytic function in here, and you have an analytic function in here. And for some of these analytic functions, there exists a closed form solution for this integral. And then what you do is all these steps are nothing else than the update of the parameters of these analytic functions. Okay? This is the case where we have, when we use, for instance, Gaussian distributions or normal distributions, where this nice bell-shaped function there. Or for many distributions of what's called the exponential family. So all the distributions you can write in terms of e at the power of minus something. Okay? We'll see later on in the class how we can model this, and according to how we model it, how we actually we perform this whole recursive estimation. Okay? Now, if you see this, you can already see like a kind of pattern. There are two steps, here and here. One is how to update the distribution considering the motion, and one is how to update the distributions considering the observation. And in fact, many filters, so many recursive Bayesian filters have this two-step implementation. So one is what's called prediction step. So we predict where the future state will be, given a notion on our previous state and how the state evolves over time. So what are the dynamics of the state? And then we have a correction step where we take this prediction, we consider how it fits the measurements that we are getting from the world, and according to the mismatch, we then update the belief of time t. Okay? And these are the two main components of any Bayesian filter implementation. Like we'll see later on a Kalman filter or a particle filter and similar. Okay? Now, we call this thing here, as I said also before, the motion model. And we call this part here the sensor of the observation model. And we'll see that there are different ways of modeling this, and also different way of then performing the update according to how these models are actually represented. Okay? Is there any questions so far? Okay. So, so how do we do it for real? This is just a framework. So this is just a container that theoretically brings you from one step to another, but doesn't tell you anything on what's behind the P. No? And there are different realizations or implementations of that, and they all depend on the properties and assumptions you make. For instance, one assumption can be if the models are linear or non-linear. So linear means that there is just an affine transformation or a linear transformation of the input to the output. And linear transformations are multiplication with a constant or multiplication with a matrix, or sum or difference between different vectors, and so on. Or non-linears, which can be any kind of function, like an exponential function, a logarithmic function, and so on. Also, which kind of distributions we use. If we only use Gaussian distributions, or we assume that the noise can come from any arbitrary distribution that can be a discrete histogram, for instance, or it can be any other distributions family, and so on. And also, if you want to do something which is called parametric filtering, where we have a function that only has a limited set of parameters. For instance, a normal distributions is parameterized by the mean vector and the covariance matrix. Or if we want to do something which is non-parametric, where by non-parametric we mean we do not have a real parameterization, so there is no analytic function behind that, but it's like an histogram, a grid, or it can be a set of samples, or can be any way of modeling a function that doesn't have one analytic parameterization. Okay? What we will do here is that we'll see two big families of filters. One filter is the Kalman filter, and we say friends because there is a lot of different extension of the basic Kalman filter to handle different type of problems like nonlinear functions, like different type of noises, and so on. And the main assumption is that the noise is Gaussian, but you cannot propagate this Gaussian noise over the motion models and the observation models because they are nonlinear function, and when you propagate a Gaussian distribution through a nonlinear function or a Gaussian random variable through a nonlinear function, you end up with a random variable which is not Gaussian distributed any longer. So they actually handle this kind of problems, but the main assumption is that all these models have Gaussian noise. And we'll see then a particle filter family where They are non-parametric, so the noise is not necessarily coming from a Gaussian distribution. There is no analytic function behind these models, and can use any kind of arbitrary model. And the way they work is that instead of having one parameterization of the probability space, they just take samples out of the probability space, and whenever you want to know what's the probability of the state being in a certain area, you take the samples in that area, and in a way, you sum them up. No? And once you sum them up, something which is connected to them, which is called the weight, you will get an idea of how probable it is that your robot is in a certain area. Okay? But we'll see the details later on. So, two important things. One is the motion model. So how do we model this? There are several ways of doing this, some more complex, some less complex. And for the filtering part, we'll use one model which has been seen also in the introduction to mobile robotics. And the whole idea is this. Ideally, you will have the robot traveling around. You just read the controls, or you just read the encoders, and everything is perfect. There is no noise, and the robot knows where it is. What happens in reality is that there is some noise, and then you end up in arbitrary part of the state space. And this noise is what we are trying to model now. So this is the distribution that we want to estimate. Again, it's the probability of the state space given the controls and the previous state. And we do it in two different models. So these are like on the lower level of complexity. You can add more things on top. One is called odometry based, and it comes from the idea that you really have wheel encoders on your robot, and then you can measure relative displacement over a short interval of time. And the other one is velocity based, where you do not assume that you have encoders, but you know which is the velocity, the command that you gave to the robot to achieve a certain motion. Okay? The odometry model is intuitively represented like this. The robot is here, is in x, y, theta, and the first thing it does, it rotates around this axis. It goes along this rotation axis, and then it rotates again. Where it comes from the fact that when you ask for an odometry measurement to your robot controller, what it gives you a displacement, okay? And the displacement that it gives you is something in this form. It gives you, I have delta x, delta y, and delta theta, okay? Now, the problem is that you cannot just apply this and sum it up to your previous vector, because these are the orientation and the xy displacement are actually connected. So if your robot is not able to drive everywhere, but it's a differential drive, for instance, where it's constrained to only driving straight, it cannot just teleport itself on a different location. So what it does is rotating, is moving towards the destination, and then it's rotating again to get the final orientation. Okay? And this is what this model tries to represent. And the fact that we need to have this different component is because every time the robot is doing one of these motions, it accumulates noise. So it does the first rotation, which is not perfect, then it does the motion along the line, which is also not perfect, and then it does a final rotation. And to account for this, we need to somehow decompose the two rotations in these two parts. Okay, so that's the basic idea in there. You can do some more sophisticated thing on top by considering what's called the manifold and knowing that there are some operations that you can do on this strange object, which is made by translation and rotation. But this is outside of the scope of this class. But if you want to have more details, just ask and I will provide you with that. How does it work? We assume that there is a normal distribution here. We assume there is a normal distribution along this line, and we assume there is a normal distribution on the final orientation. So each of these is a perfect model, which is the one coming from these formulas. But for each of these steps, we have an uncertain noise random variable, which is normally distributed. And we add it to this part here, and this part here to model the true uncertainty of the motion. here you can see what happens if we play around with these parameters of the uncertainty. In case where we have high angular uncertainty in the beginning, you can see that the robot might be everywhere in this kind of banana shape or arc-shaped part, because we're really not sure when it does the first rotation where it ends up. No? Here you have higher uncertainty in the x direction. Okay? So the robot does not know if it goes here or there. And here again, you have very low uncertainty on the distance, but high uncertainty in the angle at the beginning. Okay? So you can see how this performs. And if you want to see it in terms of sampling base, so if you want to just sample out of this motion model, you can see the same thing. The samples gets concentrated around this area, which is the darker area of this distribution. The case is the same. And here again is the same. So basically, if you want to do, let's say, a dense distribution, here is a grid with different values, and you want to know the probability of the robot being somewhere, you just take an area and you sum these values up. And in this case, you just do the same, but you have just a different set of things to measure. Here are more continuous, and here are discretized. Okay? According to the application, one is better than the other. The second model that we will consider is what's called velocity-based model. The idea here is that we have this robot, it's a point mass, he has a translational velocity and he has a rotational velocity. When you combine the two, the robot will just move along an arc, okay? If rotational velocity is 0, the robot will just move around a straight line. If translational velocity is 0, the robot will rotate on itself, okay? So that's the idea there. And these are the equations. So basically, are just the equation of a point moving around an arc. The angle here, theta, is the initial orientation of the robot, and this here is the final kind of arc motion that you get. And here you see that the angle just changed by delta t. So these are all incremental velocity vector, and in this sense, you can just have an incremental displacement. Okay. I'm not going to ask you the full detail of this whole. I might ask you actually, so it's nice if you remember them. So let's not go on. But I will try to go a bit quicker today because it's kind of a recap from intro to mobile robots. Again, one problem here is that if you just do it blindly, it might happen that actually the robot did not end up in the exact final orientation, okay? And that's because the robot might slip over time, it doesn't do the perfect arc and so on. So to model the fact that at the end it can rotate, we can either have two different motions together, where one is a velocity acceleration, so velocity, tangential velocity and orientation velocity, followed by another motion with just rotational velocity, or we can just simply fix the final rotation by just adding another rotational velocity at the end. Okay, that's just to put everything together. If you imagine that this will be the sum of different motions, when you get the final simple rotation on the spot motion, this part will not be modified and will only be modified the last part. Okay, so you can imagine in this way. But to make things simpler, we can just put everything into one single model, so you model both things at the same time. Okay, and if you look at examples, here you will see roughly the same idea with different noise. Here you have mild noise in orientation and angular velocity and translational velocity. Here you have very low noise in translational angular velocity, but a high noise in translational. So you see that you end up in a more round thing. And here again you have high uncertainty in rotational, but low uncertainty in translational. Okay, so the effect is the same, and actually at the end what the robot does when it gives you an odometry is actually implementing these things inside. Okay, because somehow the only thing you can measure is the incremental displacement of the wheels, and it translated it into velocity of the wheels, and then it integrates over time to get the real position of the robot. Okay, so at the end it's good that they represent somehow the same distributions. Okay. Regarding the sensor models, again there are different complex sensor, And in this lecture, we will focus on two types of sensors, which are mostly laser scanners and cameras. And they offer you distance with respect to objects, distance and bearings, so the angle where this object is being perceived and far away, or they will measure just bearing, so just the angle where the object is, or sometimes just distance. So they are only able to measure how far something is, but they don't know where it is, okay? And according to the sensor and according to the framework you want to use for estimation, you will have a different function here. What you have seen in the intro to mobile robots is mainly sensor for laser scanner, where we say the laser scanner has k different measurements, one for each beam where it's scanning the environment. And we assume that the individual measurements are independent, so we can write the full bunch of measurements, which is a set of different rays, as the product of each individual ray, okay? We have two main models. One is called beam endpoint model, and the idea here is that we have our beam. We only consider where it ended up. We then get the neighboring obstacles around these endpoints, and our distribution is, let's say, a normal distribution of the noise with respect to the distance, okay? So the way we do it is we take our map, or what we are trying to consider in terms of the data we are trying to measure. We just expand it with different likelihood values for each point, and the beam base will just get to the endpoint, get the value here, and gives you how likely this measurement is with respect to this environmental representation. When we do SLAM, the map is part of the state, and it's the map you have computed from the previous time steps, so you still need a kind of map to have an idea of this measurement, okay? Here you can see some real life and likelihood field, as they are called. Here is the occupancy grid. White means it's free, black means it's occupied. And here you can see how this is expanded with respect to the likelihood of each individual point and measurement. And again, if you think the robot is here, is measuring this distance, you pick up a value there and you know what's the likelihood of the measurement. One pitfall of this is that you do not consider the free space at all. So it might be that the robot is somewhere here and there's an observation there, and then you don't consider the fact that it's actually looking through walls, okay, which can be a problem because it will give you a likelihood value which is not exactly what you would like to expect, no? But in case the robot is well localized, this is actually not the big problem. A different way of considering also free space is what's called the raycast model or the beam model. So not the beam endpoint, but just the beam model, where what we...
Question.
Yes?
On the lattice field, is it the case that we cannot think about a map as a torus?
Sorry, say it again?
We cannot think of a map as a torus. If it's a torus, so if you build a lattice field, actually the Gaussian distribution never touches zero. It means if it's a torus, so when you touch an edge, actually the Gaussian distribution will continue the other side of the edge.
That is true. It depends. I mean, it depends on how you want to model things. So normally, what you do is you can imagine this as a tangential manifold on top of the torus, and then you don't have this problem, at least locally. And you can imagine that you can crop it. But actually, what you normally do is we are trying to build models of the world. And locally, all this world is kind of Euclidean, so it's kind of flat. And you can model it in this flat part as a Gaussian distribution. Of course, if you try to model all the Earth, you will have this nice sphere and so on, but it's out of the scope. You don't want to really do a full... So, I mean, you can do it, but it's not in the scope of the lecture. So it's more on the... locally, everything is Euclidean, everything is nicely and flat, or at most three-dimensional, but three-dimensional in Euclidean sense. Okay? So yeah, here we will try to model also the the free space. So we try to model also what happens when a ray is actually going through free space and then hitting an obstacle. So what we need to do is first doing ray tracing on the map, and this will tell you which is the most likely part of the environment that you will hit. And then we will put it like this is the resulting of the ray tracing, and then we model the likelihood of the beam with respect to this nominal value coming from ray tracing. How we do it? We have 4 models, and we consider a mixture of these 4 models. One first model, okay. The details on that, it's on the lectures of Intro to Mobile Robotics, but the idea here is that we have some distribution that account for something unexpected before the wall, which might be like some dynamic person moving around. We have a Gaussian at the point, which is our nominal observation, and then we model a maximum range readings from the scanner, which is at the end. Okay? Details are in the book, the probabilistic robotics book, when it talks about sensor models, and on the slides and the material for Intro to Mobile Robotics. Okay? So the last model, which is not been touched in Intro to Mobile Robotics, it's what we call a range bearing model. So here is, we have a measurement that tells you a distance from a certain landmark, r, it's the range, and phi, which is the angle at which I'm looking at the landmark. So imagine the landmark will be this corner here, and I'm sitting here. The range will be the distance between me and that, and the angle will be something like 30 degrees or so. No? So that's the idea of this. You put a 0 in front of the robot, and then you try to get which is the angle. The pose, it's in x, y, theta, as usual, from the robot. And our map stores this landmark at the position x, y in the world. Okay? This is a world coordinate frame. These are in world coordinate frame as well. So how do we predict this measurement from the robot point of view? Basically, we know that the range is just the size of the vector from myself to the points that I'm observing. So we take the difference in the x coordinates, the difference in the y coordinate, and this is the vector from me to the landmark, and the size is just the norm, the squared norm of the vector. So the squared of the difference on the x, on the y, and under square root. For the angle, we know that this angle can be computed by using a bit of trigonometry. We know that the y is the sine of the angle, x is the cosine, and if you put them together, we get y over x is actually the tangent of the angle. So we just do the inverse of the tangent, the arcotangent, and there is a function called arcotangent 2 that takes the difference in y and the difference in x and gives you which quadrant of the 4 quadrants this angle actually lies. Okay? We take this, and this is the relative angle with respect to the landmark, and then we remove the absolute angle of the robot. So this is in global coordinate frame. We translate it to the robot coordinate frame by just rotating everything back. Okay? And to this one, we just add a q, which is in this case a noise or uncertainty to this function. So we have again a random variable here. Okay? Any question on that? Okay. So if we then have only bearing, we just take this part down here. If we have only range, we just take this part up here. No? So that's the idea. So in summary, for this part of the lecture, I'll just give you an idea on what a base filter is as a framework, and I've been touching a bit what is a motion model, how you can express it, what is observation model, how you can express it, and how you can play with that. We will see later on how to use these things, but for now, if you want to have a bit more information, go on chapter 2 and chapter 5 of, chapter 2 of the book, Probabilistic Robotics for the base filter, and here chapter 5 actually means the 5th slide package, and for motion observation model is chapter 5 and 6 of the book, and the slides 6 and 7 of the motion to introduction to mobile robotics. That's it for this. We can do a 10-minute break, and then I do the second part of the lecture. Okay?